Uniform motion is the fancy name for something moving at a constant velocity. So that means moving in a straight line and not speeding up or slowing down. There's a little derivation or proof for the equation, but kind of common sense. And I think early in relative motion, we've already used the equation. This is just kind of, so we kind of went backwards. We used the equation before the proof or the derivation. Here's the derivation to show you where it came from. If we picture the VT graph for something that's going through uniform motion, it's kind of a boring graph. It's going at a constant velocity, so it's just a horizontal line. It's not accelerating, so it doesn't have any slope. One of the facts we know from VT graphs is the displacement is the area under the curve. I haven't really given you a great reason for why. It's a calculus thing, so you're just going to kind of have to trust me. Or maybe after the fact, when you see that starting with this fact leads to an equation, you recognize that the fact must be true. Otherwise, it wouldn't lead to such a recognizable equation. So displacement is going to be letter D. Area, because we're looking at a rectangle. Let's say we chop it here at some time delta t. The area of a rectangle is length times width. So letter D, the length of that rectangle, we could say that it's got a length of, we can call it V, how fast it's going, so it's going at some speed V. The width of it is how long it's been moving for, that's delta t. So there's an equation we've used before, D equals V times delta t. If we flip the t to the other side, we get V equals D over delta t. Strictly speaking, I should be putting vector hats on all of this, so we could backtrack and put all our vector hats. But velocity is what you get when you take displacement and divide it by time. There's our wee little proof for uniform motion.